Okay, hello everyone. We're going to start. This session is a modeling data session and is a mix between the MESO, GEM focus group, and CEDAR. So we're going to start with the first talk by Catherine Cariglia. Oh, perfect. Thank you.
Testing, cool. So, hello everyone. My name is Catherine Cariglia. I'm a scientific software developer at the MIT Haystack Observatory, and I'm primarily responsible for maintaining the Madrigal database. And today I'm going to be talking to you all about some of the kinds of data that we have available and how it can be useful for modeling purposes. So for folks who may be unfamiliar, Madrigal serves as the primary community resource data repository for CEDAR. And we have a huge amount of data from both ground and space-based instruments all over the world. The Haystack Observatory Atmospheric Sciences Group is generally responsible for the maintenance of Madrigal, and it's part of the Millstone Hill Geospace facility, which is supported by NSF. And over the past 10, 11 years, we've served a huge amount of data to a huge amount of users. That's about 22 million downloads to 3,600 unique users, affiliated with about 650 different institutions. So again, we have a huge amount of data, over 240 different instruments, including but not limited to incoherent scatter radar, some DMSP data, GNSS TEC data, but also things like LIDARs, photometers, magnetometers, meteor radars. We even have HAMSI data now and all-sky imager data as well. So we really try to cover all the different regions of the atmosphere that you may want to look at in your studies. Just to get an idea of how much data that actually is, that's about 83 terabytes now, which amounts to around 300 terabytes worth of backups. As you can see, unfortunately, the growth curve is nonlinear. One particular data product that I want to draw all of your attention to is our gridded ISR data, which uniformly evens out the data by space and time. So it's very, very useful for modelers because you don't have to mess with irregular data cadence, things like that. And here's an example of the web interface of how you can access this type of data and the kinds of plots associated with it. So I'm not going to get too much into how exactly to use Madrigal, but if you would like my introductory presentations from the student day, please see me afterwards and I can send those to you. There are two primary ways you can access Madrigal, either through the web interface or through the web services APIs, which are available in Python, MATLAB, and IDL. Those are very useful because they have faster downloads compared to the web interface, and you can filter data by your favorite parameters and derived parameters. So I did mention that data storage is a consideration, but resources permitting, we are always trying to be accommodating of new data types. So for PIs in the audience, there are two primary methods that you can use to get data to us. You could send data, documentation, including summary plots as well, directly to us. We'll write a loading program, which you will then verify, and you can choose to add data in either batches or via an automated upload. Alternatively, you have the option of setting up your own Madrigal site, which we will help, of course, with installation and creation of loading programs. But the best part is you get to control when the data is uploaded, and all that data will automatically get backed up to the CEDAR Madrigal repository. I also want to mention that we are on GitHub as of September 2024. So for people who want to look through the code and raise issues, please feel free to do so. I would very much love to have more eyes on things. So feel free to suggest ways to improve things. A few other updates since last CEDAR. We have some hardware upgrades, which of course has some speed improvements associated with that. We have some increased storage capacity up to 612 terabytes. The Madrigal 329 was released about a month ago. I'm currently working on a metadata backend upgrade such that we will have quicker queries and faster updates going forward. And additionally, we have several new data types. That's all I really wanted to draw your attention to, and I hope that you guys find this data and these tools useful. Thank you all for listening. Thank you so much for NSF for supporting this workshop and Madrigal. If any of you have questions, please feel free to email me. Thank you so much.
Thank you, Catherine. Wait a second for questions.
Oh, questions, yeah. Okay, gotcha, yeah.
This is an excellent resource, and it has been for the CEDAR community for so long, and it's so good that this information is also getting to the GEM community because this data is important for us too.
Yeah, we have heliophysics data that you guys would like.
More questions for Catherine? No? Too tired after the lunch? Oh, yeah.
Yeah, I would just have a quick question about the those how to say sketch plot or quick look plots.
Mm-hmm.
Are there any other options instead of this cross section, or we can choose whatever cross section we want?
Well, so the good thing about this data is that it's very easy to create a lot of different kinds of plots. So you can adjust those as you would like, and use your favorite plotting programs for that, because it's uniformly gridded in this way.
Oh, I mean the web interface. Sometimes we don't want to download the whole data and just want to have a quick look to see if there's anything that interesting. So we want to see if this latitude looks interesting or this longitude looks interesting, something like that.
So that would actually depend on the data type. This particular example does not include those parameters, but you could create those plots. So yeah, it depends on which summary plots, and which data type. Yeah.
Anyone else? Thank you so much.
Thank you.
Yeah, our next speaker is Don Lin, that I'm going to thank because I begged him to give this talk. You are just... You too? Ready to go.
Okay. Thank you, Bea. Hi, everyone. My name is Don Lin. I'm a project scientist from NSF NCA National Center for Atmospheric Research. I'm also a member of the NASA Drive Center for Geospace Storms, or CGS. So 2 weeks ago, Bea and I were both attending the Superdawn workshop, and I showed some preliminary results. And then she came to me to ask me to show some set simulations. I was referring to the set simulations as what I was showing last time. But well, indeed, that will be discussed, but I want to bring a little bit of background as well. So whatever Steve said, I agree. Okay, so earlier I think you have heard about these terminologies, Steve, SAID, SAPS, or SR-arcs together. And I'm actually more familiar with the last two terms, SAPS and SR-arcs, even though recent studies have already shown their connection, including a direct evolution from one to the other, well, maybe just from SR to Steve. I think what's in common in this phenomenon is so far mostly they are confined to the so-called subaurora region. And when we look at this classic diagram from more than 40 years ago, and also you can think about that by considering the geometry of the geomagnetic field. They do have a magnetospheric origin. And here on this plot, I'm just highlighting two most important drivers from the magnetosphere. One is about the convection electric field, which drives the convection pattern, especially the mesoscale in this subaurora region. The other is about the thermodynamic interaction, basically the heat flux due to coolant collisions between the hot ring current and the cold plasma sphere. So these are two separate mechanisms that would make a difference in the suborbital ionosphere, and they may account for the observed signatures. So I want to share the first study we published last year. Basically, this is a controlled experiment to investigate how the two mechanisms I just mentioned, basically the SAPS, suborbital convection, and the heat flux from the inner magnetosphere would make a difference in the ionosphere. So we choose an event on June the 1st in 2013, and we derived the heat flux with the semi-model, comprehensive inner magnetosphere, ionosphere model. So this one deals with a coolant collision heat flux, and I know my teammate Anthony will share some similar results from the RIGU, another inner magnetosphere model. And here is a quick validation about the results of the heat flux by comparing with violent probe measurements, and they are like with a good agreement on a qualitative same magnitude. And then we're using this heat flux to drive the TIDCM, which is basically ionosphere-thermosphere model. And again, this in the controlled numerical simulation, we can compare the net effects due to the heat flux. And at the same time, with TIDCM, we can also explore like how suborbital polarization streams work. So we carried out another controlled experiment. And so there are three comparisons here. One is a comparison of the net effects due to heat flux. The second is net effects due to the convection, and a comparison between these two mechanisms themselves. So here you can see very interestingly, so both mechanisms contribute to electron heating in the suborbital region. So this is like latitude versus longitude, and the green curves are the auroral boundary. You can see that both mechanisms contribute to the electron heating there, although with a different spatial coverage. They also contribute to electron density depletion, especially I should say variation, because the heat flux contribute to depletion, while the SAPS mechanism has like a more global impact, not only into the suborbital region. And we are more interested in the optical signatures, so we calculated the red line emission rate. Here you can see there both mechanisms contribute to the enhancement of the red line emission. So this will used to explain their role in the generation of suborbital red arc, for example. And we further analyzed their impacts in other parameters, such as ion temperature, or geoheating, or neutral. And here you can see a more drastic difference between the two mechanisms. So heat flux, since it's mainly impacting the electrons, so you don't see them changing this ion or neutral parameters very much, but the SAPS mechanism, because it involves changes in the convection electric field, so as to the geoheating, that's why it's having a more substantial global impact in the ionosphere-thermosphere. So this is a quick summary, and also the net effects in the red line from a polar view, and you are welcome to check out details in the paper. But I want to, as I promised, share some most recent results about, so finally I'm trying to connect to the Steve community, sub-community. So Bayer actually reported a very nice event in 2023, March 27th, and thanks to this typo, I was given a clairvoyant award at the CEDAR workshop. So this event was special because it occurred during relatively very quiet conditions, and so when I was looking at the driving conditions here, the only thing came up to my mind was there seemed to be there was a sudden drop in the solar wind dynamic pressure by about 40%, even though the overall background was very quiet. So I was thinking maybe during that time the magnetosphere underwent some expansion so as to generating some interesting signatures. So here's one snapshot. I think on this part I just want to highlight one thing, which is on the bottom left, the so-called Arvanic Poynting flux, simply because I was looking at that parameter during that time. It's kind of interesting to see, like, around this time, we do see, like, enhancement in organic Poynting flux at such near the auroral boundary. And we know this Poynting flux also has some heating effects. So, and another thing, based on my discussion with Toshi yesterday, was that during quiet time stable events, we do also expect tail activities that would also contribute to formation of SID or related subauroral structures. So here is a quick animation showing for this interval, even though it was relatively quiet, but you can still see some BBF-like signature in the tail. So this is something we should explore more. So as a quick summary, I think we have talked about heat flux, convection, electric field, but here I also want to emphasize the electromagnetic, including the Poynting flux mechanism. And one last comment was to really simulate a small structure like Steve, we're supposed to use nested grid or some other high resolution capabilities. I think Haonan is going to give a talk on that. So thank you.
Excellent, thank you so much. This makes me very happy. I know I have been the noise in all the modelers. Can we model this, please? So thank you. Questions for Don? You can tell it's Friday. So for the observation, I can comment at least that this event is actually very unusual. So regular Steves occur during storm time, while this is relatively quiet. And it's very interesting because, as you mentioned, we do see flows in SuperDARN, which indicates those injections in the magnetotail that Toshi was telling you yesterday. But we don't understand why the inner magnetosphere is so expanded tailward.
Yeah, I'll also quick response to that. I actually carried out a simulation for that event in Toshi's paper, 2019 February. I got those signatures again, BBF-like, so I think we can look at that together.
Excellent. Any more questions? No? Let's thank Don again.
Thank you.
So the next speaker is Prakash Podal from Clemson University. This is a student presentation, so let's welcome.
Hello and good afternoon, everyone. So I'm Prakash Podal from Clemson University, and I work with Xian Lu. So today I'm going to talk about the validation of TIGCM using data-assimilated aurora and electric field. Okay, firstly I want to start with the model structure of TIGCM. So TIGCM use different inputs as a forcing. So like as a lower boundary forcing, it use like waves and tides like to represent the vertical coupling. And for like solar input, it used like F10.7 and day of the year. Whereas if we talk about the magnetospheric forcing, so which are pretty important during the geomagnetic storms, so it uses potential and aurora as the forcing parameters during the geomagnetic storms. So we need to represent these forcing parameters properly in the model if we want more realistic simulation. So if we have more realistic forcing, then we get the improved simulation. Okay, so we know that the inputs in TIGCM, but here I want to talk something about why we need data assimilation. So actually, if we talk about the ionosphere-thermosphere system, then IT system is multi-scale. So if we see one type of pattern, if we look from, if we observe from like, from some, okay, so if we, so we see like one type of pattern if we look around the range of like 1,000 kilometers, for example. But if we zoom into the mesoscale, like around 100 kilometers, then we see like different types of patterns. So it is a multi-scale. So and other is the empirical models which we have. They only reproduce the large-scale structures, so which restrict the proper understanding of IT regions at different scales. So here is the example. So the one here, I have shown the Themis and auroral modal energy flux for one of the storm case of February 20 at 5:20 UT. So if we see the observation, we see the intensified and structured aurora, but the model, it do not have such type of mesoscale structures. And here is the example of the observation of electric field. So the blue is from the model, and the red is the Pfizer observation. So we see that the Pfizer electric field show more variability and high peaks compared to the model. So if we want we aim to include these real data to drive the model and see the response. Okay, here I want to introduce the lattice screening data assimilation approach. So it is actually, so here the observation, we get the observation by adding spatial mean and spatially correlated vector with the error term. So this spatial mean we get from, statistical mean we get from the background model. And this spatially correlated field, so it is the weighted sum of covariance and the basis function, and error we get from the observation. So here I have shown the example like how the simulation map look if we incorporate the observation and the model. So this is the energy flux at 6:55 UT of March 24, 2023. So for my work, so which I am presenting today, I use the observation of aurora from the DMSP SUSI and Themis all sky imagers. And as the E-field observation, I use Pfizer and Super10. Whereas as an empirical model, I use the auroral model made by Zhang and Paxton of 2008, and Super10 spherical harmonic fitting potential model as my empirical models. Okay, so this is the aurora and electric field maps which are seen after the assimilation. So if we look at the top figures here, the energy and flux are these are the empirical results, but after data assimilation, so we see like the more structured maps, so which consist the data. Similarly, if we look at the electric field, like the first column are the empirical data, empirical maps, whereas like after data assimilation, after incorporating the Pfizer electric field, so we get this intense electric field structures in the Pfizer location. So compared to the empirical models, the assimilated maps show finer structures and offer more realistic representation. Okay, so we use this map to do the TIGCM simulation, and this is the result at the Pfizer location. So the right side is the observation, whereas left side is the simulation. So compared to the default run, so if we compare this, so the first one is the electron density simulation. So the first figure is the default run, where I have not incorporated any data. But after using the electric field and aurora, and if I do the simulation, then I was able to capture this E-region density enhancement, but which is comparable, which we can see in the observation also, but there is some limitation too. The electron density are overestimated. And if we look at the ion temperature, then this temporal and particle variability are captured, but still the model overestimate the F-region ion temperature if we compare with the observation. And if we look at the electron temperature, we see the variability which is captured compared to this default run, but still the model overestimates the electron temperature in F region. So that is the limitation of the model. Okay, so this is the TIGCM simulation. So we look at the global scale also, like how the model works and TIGCM respond to the data assimilated aurora and electric field. So this all result are after the data assimilation. So this is for the quiet day. The second one is the storm day. And the first figure is for the O by N2. So we see that there is a depletion of O by N2 during the storm if we look from the observation. So which is captured in the simulation result also. But the spatial extent of O by N2 depletion is around 20 degree here. So which is different from this, what we observed from gold. And also there is the underestimation of O by N2 in low latitudes. If we look at here, the O by N2 is high during the storm day as well as in quiet days if we look at the observation, but that is underrepresented in the simulation. But the strong point is we were able to capture this depletion in O by N2 in high latitude regions. And similarly, if we look at the neutral temperature, then the simulation result, it represents the increase in neutral temperature in response to geomagnetic storm, but still it overestimates the day side heating because so these color bars are at the same scale, so there is no heating, more heating in the observation, but there we see the heating in our simulation. So this is at the day side in the local time. Okay, so it overestimates the day side heating, and also like the spatial extent of the simulated heating is too broad in northern hemisphere, which is compared to this compared to the observation. Okay, and so this is the last result, which is of TEC. So we also observed the TEC. So the model reasonably it captured the quiet day TEC in both magnitude and spatial distribution. So here the blocks it represent. Here I have highlighted with the blocks, so they are captured properly. But but in the storm day, so we didn't see like more like total electron content, but from the observation, but the simulation it overestimated the storm day TEC. And also it failed to capture the negative storm impact, because if we compare with, if we subtract the quiet and storm day, we see that the quiet day have a high TEC compared to the storm day, so what we call as the negative storm impact. So that is not captured by the simulation for this event. Okay, here is the summary of my talk. So I saw that the data assimilation improves the storm time modeling of IT system, and it captures the key features such as E-region enhancement, vertical and temporal variability in electron and ion temperature in local region, and O by N2 depletion and increased neutral temperature at high latitude. And it also represents the quiet day TEC. But the limitations, it also have the limitation, like it overestimate like electron density, temperature, and the extent of O by N2 and temperature is broad compared to the observation, and it fails to capture the observed TEC reduction during the storm compared to the quiet day. So as a future work, we will explore the sensitivity experiment by varying the magnitude of electric field and aurora energy input to assess the impact in the IT response. Okay, thank you. And so if any questions or feedbacks, please.
Any questions from the online audience, online and the in-person audience? Well, if no questions, I just have a very brief comment on the data availability thing. Since data assimilation is not just a model, it's mostly still data. So if we are missing data, then we don't really do a very good job in data assimilation. So that causes our need for providing more data sources, meaning putting more instruments on, both on the ground and in space. So that's my comment.
Thank you.
So, thank you. Thank you, Prakash. So the next speaker is Anthony. And Anthony is going to talk about the SAR arc simulation using Raiju.
Great, thank you very much. This may look like deja vu to some of you that were in the session this morning, but hopefully seeing it a second time will help get some more out of it. So I'll be talking about some of our recent modeling work, trying to connect storm time SAR arc variability to mesoscale ring current plasma sphere evolution. This is very complementary to what Dong was talking about earlier. He definitely helped out a lot by giving some intro to what star arcs are, but just to add a couple more sort of aspects in the context of this talk is that one, they are generally below the diffuse spheral oval, and they're associated more with recurrent protons than with the electron population, and that they're very narrow in latitude, but very expansive in longitude. But the thing that we're really interested in is kind of summarized on this slide is we know that the miniospheric drivers for star arcs, whether it's the Coulomb collisions or the heating of those cold electrons via emic waves, are both driven by overlap between the ring current and the plasma sphere. And so when you combine that with the fact that star arcs have actually been shown to exhibit a high degree of spatial temporal variability and multiplicity during storms, as demonstrated in some of these examples here from a really nice paper sort of summarizing it, this sort of indicates that we have these really complex interactions between these two magnetospheric source populations during storms, and we want to understand exactly what's happening there, because it's still, the connection hasn't been made yet, whether these structures in star arcs are coming from variability or structure in the ring current or the plasma sphere, maybe both, or maybe one in certain situations, the other for different morphologies, but then also what the underlying magnetospheric processes are that are leading to that structure in the first place. And so what we're kind of interested in doing is being able to develop this understanding and connection between the two so that we can use the expansive set of ground-based observations we have to understand what's going on in the magnetosphere during these storms. And so modeling can be a very big help with this, since we don't always have the right conjunctions at the right times and locations for this, so modeling can help us build this intuition, but it's really hard to get at this because these are already very fine structures, being just 1 degree in sort of height, and then you're adding structure on top of that. And so that is one of our main motivations for the development of this new magnetosphere model that was mentioned earlier, which we are calling RIGU. That stands for the ring current advection integrated over J and mu. You can tell which one we came up with first. But this is essentially a successor to the Rice convection model, or RCM, for those that are familiar. It's using the same physical formulation as an RCM, but we've rewritten the entire model from scratch. And very importantly, that includes the core solvers that we're using very similar techniques to what are used in Gamera, including higher order reconstruction. That lets us get more sort of structure out of the grid cells that we already have, but then with a bunch of other improvements, we can not only have more grid cells on top of that, but also pack them in the auroral region to really get down to the spatial scales needed to resolve these features. And this is now integrated into the MAGE model that's available on GitHub. And so what we're going to look at today is a case study of this double peak star arc observed during the November 4th, 2021 storm, commonly referred to as the Panamanian Flag Day storm. It's actually during this initial period of just after SSC. And I'm just sort of showing what it looks like in the simulation. Right here is a snapshot. I'm not going to show the whole video for the sake of time. But on the left side, I'm showing the ring current pressure in blue, and these green contours is the plasma sphere density. And then on top of that in red is the heat flux due to Coulomb collisions, which are being calculated self-consistently within the model. And we can see in the equatorial plane, and then also in the ionospheric view, this double peak star arc that looks very familiar to this structure in the middle panel here. And so our goal was to try and figure out, since we saw that, what was leading to that. Before doing that, it's just a quick data model validation. On the left, I'm looking at a kilogram taken along this slice in latitude here as a function of time, where we can see a little bit after storm onset, about an hour or so, we get this sort of first peak down here, and then a little while later the double peak, and then these sort of persist and follow each other for quite a good amount of time. And that not only is each peak getting close to about that 1 degree in width on its own, but the separation is about that scale as well. And this is a preliminary comparison to Millstone Hill data retrieved from Madrigal, and this is showing 2 snapshots of this faint double peak. Star arcs can be very faint. And then down here, I've done a sort of, so far, uncalibrated keyogram, just sort of using the GIF here, but we're working with the experts at Millstone Hill to get the calibrated versions and do a better one-to-one comparison. But we can at least have some evidence that this was actually something that was occurring during the storm itself. So, so the next question is, what is causing the double peak? On the right here, I am again analyzing variables across this arc and latitude, which is on the x-axis here. Up top, I have the proton intensity in the magnetosphere as a function of energy, which is a very common thing for us to look at. But then I also have the heat flux from Coulomb collisions also broken down in terms of energy. I do have it in units of a per keV, so the higher energy stuff is actually contributing more than it appears on this panel. But then on the bottom here, I have essentially this value of integrated in energy to give you that total heat flux there. And then coinciding with that, the plasmasphere density there. So you can see how we're sort of tucked into the plasmasphere itself. And so to sort of direct your eye to 2 main features here, there's sort of 2 major contributions. One is this radially dispersed dusk side ring current, where you have this peak here happening around 58 degrees latitude. But because of this really long tail that gives you a sort of broad initial peak, and then what you actually have is this fresh energetic injection on top of that, which overall is only giving you 30% of what's there along the background, but that's enough to make the second peak sort of stand up on its own there. And so this is just sort of showing you how that happens instead of just stating that's what we're looking at in that panel. So here we have, before we developed the double peak, the pre-existing ring current, and this right panel is showing that proton intensity along the red line here. If we go about 15 minutes later, we see this relatively fresh injection has already started to disperse a bit, but it's a new addition to the ring current population, and it doesn't show up too strongly on here, but that's you can see that actually feature in the proton intensity, and then as time goes on and all of this drifts duskward, you get that population we were just looking at. And so to talk about this radial dispersion really quick, that's happening, so you can see in these top panels you have all these energies sort of stacked on top of each other, and then moving into the dusk side is what's creating that broad base for the injection to sort of stand on top of. And if we look on this side, if we compare the E cross B versus gradient curvature drifts, you can see how you have the lower energies following that E cross B further out, and then gradient curvature drift pushing the higher energies closer in to give you this space right here, and then when you add in the injection on top of that, is able to form that double peak in this situation. So to sort of conclude or summarize it, connecting star arc variability to their magnetospheric drivers can be a very powerful means of understanding in-magnetosphere dynamics, particularly because it's really difficult to do this with in-situ spacecraft alone because they're flying through the region very quickly. They don't have the sort of less localized view, and we can monitor these things evolving on hours-long timescales, which is also really hard to do with in-situ because you kind of come around every few hours or so you don't know what happened in the meantime. But to build that understanding, high-resolution physics-based modeling can play a really a critical role in helping us achieve that. In this case, for this double peak star arc, it's seeming to come from structure in what's going on with the ring current protons. But we can also see, just in this video here, that you see a lot of structure in the plasmasphere in green, also affecting where this heat flux is occurring. And so this is evidence on its own of some cases being due to ring current structure and others being due to the plasmasphere. And so we want to explore this more in the future and sort of build up a better intuition about how those specific phenomena we see in star arcs correlate to what's going on in the in-magnetosphere here. And I have some more points here, but I will leave it at that, and we can go into them if people are interested, but we can take questions here. So thanks.
Any questions from audience?
back to your simulation and data slide.
Yeah, this one?
Yeah, so for the simulation, and this might be me because I'm tired, I can see the double peak. Can you point at it?
Oh, so it's just these right here. So it's not, there's still some elevated heat flux in between the two peaks here. It's not going away completely. But yeah, so this would be peak 1 going along here. It gets disrupted a bit here. And then peak 2 is more along the poleward edge up here.
And in the observation, the lower latitude peak looks very, very faint.
It does seem much fainter, yeah. And so we're working with Carlos to get the calibrated versions and to make sure it can stand out as much as it can for the validation, yeah.
That's awesome, thank you.
Yeah.
Well, I have a question on the last slide, the summary slide, that movie. Can you explain what is this breathing or trembling mode of this this motion?
Along the outside here?
Yeah.
Yeah, so I think this is related to just convection and SAPS in that region. SAPS is known to not only erode the plasmasphere on this side, but also generate these undulations. And so that's giving you your plasmasphere density. You can see outlined in green there.
What kind of this breathing mode, oscillation, what's the period of that?
That's a good question. I have not analyzed that yet, but Cream can probably help more with this.
Yeah, I think for some of that, it's also just variations in the solar wind creating compressional waves that are jiggling everything in the intermagnetosphere.
Any more questions? Thank you, Anthony. That was great.
Thank you.
So our next speaker is Jingyuan Feng, and this is a student presentation too.
Hi everyone, I'm Jianyuan Feng from Wuhan University. I'm a PhD student and currently visiting the HAO. I'm here to talk about the topic of the overview of very low frequency measurements. So as we know, ionosphere has 3 layers: D region, E region, and F region. D region is the boundary of the lower atmosphere, and the higher ionosphere. It corresponds to the altitude range between 60 and 100 kilometers. It's a very special region that the altitude of it is too low for satellites, radars, but it's too high for balloons. So it's still one of the least explored region in the geospace. So how to monitor the D region? I would say very low frequency signals. The frequency range of the very low frequency signals is from 3 to 30 kilohertz. There are two main sources in the geospace. One is the lightning activities, and the other one is the artificial very low frequency transmitter signals. The VF waves bound within the Earth and ionosphere waveguide. It can carry directly information about the lower ionosphere. So it has been turned out to a very effective way to probe the lower ionosphere. We have developed a very low frequency signal detection system. You can see the lower panels, that there are some horizontal lines with fixed frequencies. It responds to different transmitters, and we also can observe the lightning signals in the received data, and also the twig cross like this. And we have set up the very low frequency waves detection network already in central China and Antarctica. The range covers from 2016 to till now. So it's already collect over 200 TB data. So what can very low frequency waves tell us about the space? The first is the solar flares. That's the data we recorded in Antarctica. The transmitters are in North America and Europe. We can see very clear response of the very low frequency signals during the solar flare. So we can analyze what happened in the lower ionosphere during the events. And the eclipse, both of the amplitude and the phase can be influenced by the eclipse. So we can use the model and observation to see the variations of the region. Because the position of the region is very special, it's a boundary between the upper ionosphere and the lower atmosphere. So besides the solar activities like flares, eclipse, storms, and the factors from the lower region can also influence the region. So this slide is about the relatively longer term variations. We observed the periodic variations of very low frequency signals. The periods ranging from 2 days to 2 years, and they have the common periods like 5 days, 10 days, 16 days, 21 days, and a year, which related. We suppose that they are related with the planetary waves, SO and QBO. And we also analyze some short-term variations as well, like the gravity waves. These the results we decomposed from the very low frequency signals recorded in Antarctica, and we can see we filter the wave-like disturbances between the 4 minutes and 1 hour, and we can see that they also have some semi-diurnal and diurnal variations, which might be related with tides. And besides the natural source, the artificial factors can also affect the region, like rocket launch. So we find some cases that very interesting. One of them is the case in 2022, August 4th. The New Shepard rocket left it from the Florida, and we observed the 2-stage abnormal variations during the rocket launch, and they have the periods like 3.5 minutes to 7 minutes, and the velocities are at the level of kilometers per second, which is consistent with the shock acoustic waves. So that's the summary. The D region is a very special region. It can not only influenced by the solar radiation, cosmic rays, and particle precipitation from the upper region, but the atmospheric waves from the lower atmosphere can also affect the status of the D region. And the very low frequency transmitter signals is a very suitable and unique way to probe this region. And furthermore, we can monitor the propagation evolution of atmospheric waves, and some other space weather events with more detectors. So if you are interested in the region or very low frequency signals, please feel free to contact with us. And thank you, that's all.
Thank you so much. Go ahead.
Hi, nice talk. I was wondering if you have ever seen or looked into VLF effects from energetic precipitation, though your path lengths might be too low in latitude to see it.
I'm not sure because we have the receivers only in central China and Antarctica, and the transmitters position are already they has running long time, so we are not sure that about the transmitters.
Thank you.
Any more questions? Thank you so much.
Thank you.
Our next speaker is Anusri-Devanandan, and it's a student presentation too. Sorry for the mispronunciation of the name.
So hi everyone. Mine is also a presentation that's very similar to the one that I presented in the morning. So I'm Anusri. I'm a graduate student at the University of New Hampshire. This is the work that I did with my advisor and some of the CGS team members at APL. So these are some of the results of our analysis of bursty bulk flows during geomagnetic storms. Some of the previous studies have shown that plasma sheet has an elevated BC and convection electric field during geomagnetic storms. Here is, on the right-hand side, you can see a plot from Raptis et al. 2023, where it shows the median difference between the EY values, convection electric field values, during main phase compared to the quiet time. And the arrows indicate the direction of plasma flows, and the length indicates that magnitude. So as it can be clearly seen, the convection electric field is higher during geomagnetic storms in the plasma sheet. And bursty bulk flows, as most of you already know, are fast transient flows, which play a crucial role in the total plasma sheet transport. So we wanted to see how they behave during storms and how these plasma sheet conditions affect the BBEFs occurring during geomagnetic storms. So we used the data from GeoTail mission from 1994 to 2022. And to select a BBF interval, we used a couple of criteria that are shown here. So for an interval to be qualified as a BBF interval, we required that the perpendicular flow velocity, which is the x component of velocity perpendicular to the local magnetic field, to be greater than 100 km per second throughout the interval. And there should be at least one point within this interval where V perp x is greater than 250 km per second. And to ensure that the spacecraft is within the plasma sheet, we required that the ion beta is greater than 0.5 and density is less than 5. And all these measurements were made within -15 to 15 Earth radii in GSM Y coordinate and -5 to -31 Earth radii in GSM X coordinate. Using all these criteria, we identified approximately 2,500 BBF intervals in the plasma sheet, of which 88 are main phase, 254 are recovery, and 2,152 quiet time intervals. And we performed a superposed epoch analysis of these intervals, separating them into main, recovery, and quiet time intervals, with the zero epoch defined as the time when V perp x is below 150 km per second before it exceeds 250 km per second. So here is a plot of the median of all the superposed values during main phase, recovery phase, and quiet time of all the BBF intervals we identified. Black is quiet time, red is main phase, and blue is recovery phase. The first panel is the perpendicular flow velocity. As you can see, the values of the perpendicular flow velocity is kind of similar for all the BBF intervals during storm time and quiet time. When I say quiet time, I mean non-storm time. To ensure that this is not an effect of calculating the median, we looked at the percentile distribution of these of the velocity of these intervals. Here is a plot of the median and the 75th percentile, and as you can see, the perpendicular flow velocity values are somewhat similar for all the intervals, regardless of the geomagnetic condition. So going to the next panel, we have BZ. A sharp dipolarization is observed at the zero epoch, and BC remains elevated for all the storm time BBF intervals, with the main phase having a higher BC compared to the recovery and quiet time. And this is due to an elevated magnetic field in the plasma sheet during geomagnetic storms. Moving on to the next panel, which is minus V cross B or minus V cross BY, or convection electric field. We observed a sharp increase in the convection electric field at the zero epoch, and main phase BBF intervals are observed to have a higher convection electric field compared to the quiet time. And to analyze it further, we removed the background values, which means we calculated we calculated the difference of the EY values from the mean values before the zero epoch, and just to see the contribution of BBF to the total magnetic flux transport, or the flux transport by BBFs. And we still observe an increase or an elevated convection electric field during the main phase. To see the contribution of the velocity and the magnetic field components of this, we did a superposed epoch analysis of this expression, where the delta values indicate the relative difference between the, of these parameters from the mean value before the zero epoch. So the first one shows the delta values of EY, and the second one is delta V dot B, third panel shows V dot delta B, and the fourth panel is delta V dot delta B. As you can see, the second panel, that's delta V dot B, is observed to contribute more to this increase in the convection electric field during main phase. So the overall increase in the convection electric field by BBFs is contributed, the main contribution comes from the increase in velocity, but this difference in the convection electric field during main phase and the quiet time intervals is a result of an enhanced magnetic field in the plasma sheet during storms. So moving on to the last two panels, which is density and temperature. During quiet time, you can see a drop in temperature at the zero epoch, and the temperature is observed to increase, but this trend is not very clear in the main phase and recovery phase intervals. So we divided these intervals into those BBF intervals which are observed during storms driven by ICME and storms driven by high-speed stream events. So what we observed is that BBF intervals during ICME-driven storms are observed to have similar densities during main phase and recovery phase, and temperature too, but during BBF intervals during high-speed stream-driven storms, they have, we observe a lower density for recovery phase intervals and a higher temperature for recovery phase intervals. So to quickly summarize, we observed that the properties of storm time BBFs related to their background are very similar to those observed for non-storm time BBFs. And we observed an elevated BZ throughout the epoch window for storm time BBFs, which is mainly due to an enhanced magnetic field in the plasma sheet. And comparing non-storm time and storm time BBFs, the relative increase in the convection electric field during the main phase is primarily due to an elevated magnetic field in the plasma sheet. So yeah, our future work is to do a similar analysis with Themis data, and also we are planning to look at the occurrence of BBFs at dawn and dusk and compare it to the results from simulations. That's it. Thank you.
Oh.
Hi, great talk. Just one question about when you're doing all those statistic events or statistics of your events, are you separating, like if you see burst ball close in, so typically you'll see multiple like over a storm period. If you see like one and a second one in that same storm period, are you separating those or are you combining them both into the?
So we made sure that there are no BBF intervals within 5 minutes of each other. So yeah, more like isolated. I would say within 5 minutes, not in the same storm period, but yeah.
Okay, that it just seems so. I just looking at BBFs a lot. I see sometimes even within not 5 minutes, but like 10 or 15 or 20 minutes, and the second and third BBFs, if you see them, would still be already traveling through a somewhat dipolarized field. So I would just say maybe look at how your BZ jump changes, whether you're looking at the first one or like a second one or like a third one in a group.
Oh yeah.
I think that'd be interesting.
Thanks.
But great talk.
Any more questions? If not, let's thank our speaker again. And the next one is Eric Donovan from University of Calgary, talking about the track Aurora dataset.
Hi, everyone. As said, I'm Eric Donovan from the University of Calgary, and there's probably not a lot of reason for this talk at this point after this meeting because there's been so much T-Rex data shown at this meeting, but it's always good to take any opportunity we're given to bring it up front. T-Rex stands for the Transition Region Explorer. It's a ground-based program. I'll come back to that in just a minute. I want to show that at the University of Calgary I've been there for 30 years, but for the last 50 years, researchers at the University of Calgary have been using and developing ground-based systems to remote sense what's going on in the aurora, the upper atmosphere, and then increasingly to take that and use that information to talk about what's going on in the magnetosphere. And this is just some figures from our recent decades, and the kind of thing that we do is we have the Themis white light imagers, and then we might take, this is a couple of channels from the meridian scanning photometers that we operate, where you look at the red line and the proton aurora. And we can look at boundaries in the red line, the poleward boundary for, as a proxy for the open-close boundary, the poleward shoulder of the proton aurora, of the bright proton aurora as a proxy for where the magnetic field goes from more or less tail-like to more or less dipolar, and then to use these things to talk about locations in the magnetosphere as they're projected in the ionosphere, and then also magnetospheric dynamics as they're projected in the ionosphere. T-Rex came about starting in about 2014. We proposed this, we started to push towards this project, and the idea was we had Themis ASI, and we had Canopus and Northstar in the past. And the idea was to take a 3-hour MLT chunk of land in the central part of Canada, extending from about 58 degrees geomagnetic up to about 71 degrees geomagnetic, and then to cover that with imagers that are imaging in the oxygen red line, near infrared, the blue line, and then we also installed full color imagers from which we extract, among other things, the green line intensity, and then to anchor that with meridian imaging spectrographs, and we have 2 of those which span the entire latitude range, but right in the center of the array, and then to augment that with GNSS systems and imaging rheometers. And everything has been in place now for more than a few years, except for the imaging rheometers, which are coming online now, and they've been the most challenging part of this development. The idea was also, and Emma has spoken about this earlier in the meeting, where we wanted to get away from we wanted to move away from people having to go to the data directly if they didn't want to, and then to derive products, which are really the things that we're after. It's like we're not, as researchers who are interested in MI coupling, for instance, or ITM science, or any number of things, we're not so much interested in the brightness of the aurora as what we can extract from the brightness of the aurora in different wavelengths, for example, about the incident energy flux or the characteristic energy or what's happening with the conductivity and so on. And the idea was to build up a data cube, where that data cube was 2D maps of different parameters that one would infer from the T-Rex data. And we've been working towards this for years, and this has been, I would say a labor of love on the part of people like Emma, Jun Liang, who's put a huge amount of work into developing what he calls the T-Rex auroral transport model. One of the things that the whole point we want to make here is that we're trying to look into the magnetosphere and to talk about magnetosphere-ionosphere coupling. And this is a projection of the RGB data, which you've seen a lot of at this meeting, where we want to be able to relate the dynamics that we see in things like the RGB data to dynamics in the geomagnetic tail. As I said, Jun Liang has been working on developing T-Rex ATM, the auroral transport model. And now we have this set up so that people can reach into this from outside using our API, using either Python or IDL tools, and then to take the T-Rex data and then to infer things like what you're seeing here, like a map of incident energy flux. And the idea is we're trying to bring our data from our observational system to meet the modelers in a way that makes the connection between the modeling and the simulations and the observations more, a richer landscape to play around in. And Kareem's nodding, I think, and it's always just one of these things where when we start to do this, it seems like, yeah, we'll do this next year, and that was like 10 years ago, but we're getting there, okay? And I think we're making progress. And then in the last year, a year ago, actually, from right now, because we brought this to GEM last year in Fort Collins, but Josh Houghton, who a lot of you know now, Jun Liang, Darren Chaddock, who was here, Emma, then that was really that team, did a huge effort last year to transition us from the way we had been doing things to a more, I would say, state-of-the-art way of doing things. And I invite people to go and look at our University of Calgary Space Remote Sensing Open Data Platform, and that's Emma's and my research team's open data platform. And on there you'll find things that point you into our data archive, documentation about our data sets, working with our data, and that really is looking at the crib sheets and other tools that enable one to start using our Python codes or our IDL codes and our API. And then data discovery. And I just want to say a couple things about data discovery. We've also been doing a lot of work on this, and people will know about Swarm Aurora, Aurora X, and Aurora X. And this is really part of all of this is a virtual observatory. And I would invite people to go to Aurora X, and then to go to the different tabs, like for instance the virtual observatory. We have Geogrammist and the Event Explorer, and these are ways that you can look at the data in interesting ways and extract things like movie clips and tune them yourself to how rapidly they play, how long they are, and so on. And in fact, I had come up with the idea of what became Geogrammist because I'm always looking for a market to cater to. And this Geogrammist is perfect if it's the night before you have a talk, right? It's the night before, and you don't want to show the same movie you showed last year, right, or the last 7 years. Like we've all done this, right? And so, but you want to find a new movie, but you got no time, right? So Geogrammist is perfect, right? Because you stack plots of Geograms, and you can clip out times, and then you can look at the movie, and then you can tune the movie yourself in about 5 minutes. That was my marketing play for getting more of our movies up on there. And then the Event Explorer, I'll finish with the Event Explorer, which is really our attempt to take what you see in Swarm Aurora and turn that into a 3D viewer, right, where we're projecting things like images on the map, because in Swarm Aurora we don't project images on the map. This is actually a 3D globe that you can spin, and you can show trajectories of satellites or their footprints, say at 110 kilometers in 3 dimensions, and then and then explore that through I would say a fairly intuitive interface. And I'll stop with that.
A question or comments for Eric?
Thank you. Thank you also for putting all these data sets into one place that's easily accessible. It's really helpful for early career folks like myself.
You're welcome. You're welcome. They've always been in one place, but they weren't easily accessible. So,
well, thank you still. I was wondering, this Event Explorer tool is really cool to play around with, and it's been fun to see the highlighted events. I was wondering if you have an estimation of when the rest of the data set would be available to be up and running.
Well, if you asked me 5 years ago, I would have said 3 years ago, right? So, I mean, this comes in bursts of work, right, that are driven by something. And so if you were to, for example, communicate to Emma that, there was some pressing strategic need to move that along because of some upcoming, for instance, Nightside Transition Region workshop. This can happen quickly, but it needs someone like Darren, in particular Darren, to be able to carve out a couple weeks to advance something, right? And so certainly within the next few years, but you can contribute to pushing it along.
Thank you.
Okay.
Any more questions or comments?
I just wanted to comment that your group developed all the tools, the analysis tool in Python and IDL, and that the CEDAR folks might not be very familiar with. But if you go to the documentation page that Eric mentioned, it's very, very easy to follow along and to play with the data. So I encourage you to do that.
Yeah, if you just Google UCalgary space remote sensing data, this comes up as the first hit.
Yeah, following Bear's suggestion, I also would like to suggest you promote more to the CEDAR community, because I believe most of the CEDAR people are not very aware of this new data product.
Yes, I have been asked once, how can I find this in Madrigal? And I'm like, it's not in Madrigal, it's beside Madrigal. But I would say this does point out something, right? Because we're in Canada, and we have, as everybody, limited resources. And so we tend to go to GEM, right? Because we're largely, in Canada, magnetospheric driven, as opposed to ionospheric and thermospheric driven. And certainly not mesospheric driven, but Larry Lyons and I were talking earlier, and I really love having GEM and CEDAR together. Like it's really because for people who go to GEM, having that overlap in sessions with CEDAR is huge, and I think for people who are in CEDAR, having that overlap. And so I when I was GEM steering committee chair, I used to think, I don't know why we don't just do this together. Like, why is that not the rule? And it doesn't have to be together, like the whole thing. I kind of like the idea of having 3 or 4 days of overlap, and then 2 days of GEM on one end and 2 days of CEDAR on the other, because there really are GEM people who aren't CEDAR people at all, and CEDAR people who aren't GEM people at all. But there is this big chunk of overlap, and it would be nice to more programmatically cater to it, so that that would address your thing right away. But we just don't tend to go to CEDAR.
But it doesn't hurt if you send out a CEDAR email list.
Yeah. I mean, I didn't say I was. We will do that. Okay. Okay.
So, very quick clarification questions. I think I saw red and blue. Do you have green at all?
We don't have green, but what we do is we have these RGB full color imagers. And then Jun Liang, and they're very specific, like it's not like just taking any DSLR or whatever. They're a very specific set of detectors that are very well characterized. And then Jun Liang he's published a paper, I can point you to it, I just don't have it here, but Jun Liang has done a paper where he has demonstrated we can extract the green line intensity from our RGB data. So they give us green line images. It doesn't always work, but we can tell from the data when it won't work. Right, so that's the nice thing is that you can look at the data and go, it's probably not very good now. And if you want to know what, I mean, like the reason why this works, right, is that the same reason why Christine Gabrielson and Toshi Nishimura's work on getting conductivity from the Themis white light imagers, right, is that, if you just assume most of the luminosity in the white light imagers is from green line, you're usually right. Right, and so it's just the brightness and the crispness of the green line intensity that allows us to do this, and its dominance over other things, right? And it's pretty good. I mean, the correlation is really good, right? So we have green line images, if that helps.
If no questions for Eric, let's move on to the next speaker. Next is Joe Tibet. He is also a student presenter, and he will be talking about the ENA OSIM experiment.
All right, hi everyone. If you were in the earlier morning impact session, you've seen most of this already, but maybe it'll be nice on the second time around. What I'm working on here is essentially developing an observing system simulation experiment for a kind of magnetospheric imager known as an energetic neutral atom imager. I'm just going to call it an ENA imager from here on out. First thing I want to say is that this video should have Sarathia et al. 2021 Frontiers next to it, but PowerPoint made it jump to the front. So Anushree already gave a great introduction to the features that we're looking into studying with this technique, so I won't go into detail on that. But I will say the general goal of this project is to investigate the sort of science questions around how effectively could we use an imaging technique like this to identify the spatial extents and temporal characteristics and other energetic components of things like bursty bulk flows and other transient phenomena in Earth's magnetotail, which are pretty important during geomagnetic storms and substorm times. Energetic neutral atom imaging, the short version is that if you have a bunch of plasma that slams into the exospheric hydrogen or neutral population, these ions can steal an electron and become neutral, and maintaining most of their momentum, they keep most of the energy they originally had, so you can measure these remotely and trace them along lines of sight back to where they came from. So I mentioned that I was going to be doing an OSSI, so what this means is that I'm simulating a virtual instrument inside of the MAGE simulation environment. Here, I'm using a very ideal imager setup, which by that what I mean is that the synthetic imager is pointing nadir from a high polar orbit of about 7 RE, and I'm projecting all of these images down into the equatorial plane. So essentially this is meant to be a starting point to sort of give an upper limit on what is the best sort of result that this kind of line of sight integrated imaging and all of its caveats could tell you a story about in terms of the overall picture of this magnetotail transport. So I mentioned that we wanted to track some of these features, so here's how we do that. A simple way of doing it is to take the high and low energy flux spectra from the energetic neutrals that are emitted by the plasma. I, again, reproject these down into the equatorial plane, and you can see that there's a feature fairly sort of well outlined there in the high energy and the low energy too. If I take the ratio of these two things, it essentially isolates anywhere where there's bulk acceleration of the plasma feature, and you can throw contours on top of one of those maps, and that'll give you some sort of a hard boundary that you can track just for a rudimentary projection of where the feature is. So here's a quick test interval that I'm using here. This is from a MAGE simulation of the St. Patrick's Day storm of 2013. Here you can see on the left-hand side a slice from the equatorial plane showing the residual magnetic field. This shows a structure that makes its way in around midnight, lasts a few minutes, and then eventually sort of dissolves and fades away as you get this sort of broad, strong dipolarization happening in the magnetotail. The right-hand side shows that so-called flux ratio quantity that I mentioned, which is highlighting where there are regions of this acceleration and sort of enhancement of higher energy populations. Now, you can see that although the sort of motion of the image projected into the equatorial plane here tends to match the overall motion of the feature, it's a little bit stretched tailward, and that's one thing I want to talk about here. So here's just a quick result on tracking this feature in terms of its radial position. The blue line here on the left-hand side is the imaging data, or the synthetic imager data that I've projected to the equatorial plane. I'm tracking this particular feature right here, and you can see it right at this moment of roughly closest approach to the Earth. The contours that are sort of orangish and yellow on here correspond with this orange line on the left-hand plot, and I'll let this play out as well I talk. You can see that the contours themselves are derived from an equatorial slice directly from MAGE. And the reason we're doing that is to give a good baseline against which to gauge how well the imager can define where the actual spatial limits of these features are. And so although the inner radial extent of the feature, especially close to the moment of closest approach, is decent, the overall picture is a little stretched and distorted, and the blue pixels essentially don't line up too well with the contours, or not as well as we'd like, at least. However, both of these, the ground truth and the imaging data, tell the same story of a feature which approaches Earth, decelerates, stops, and then rebounds, and eventually becomes difficult to track. So how can we improve this tracking? So option one is add another imager. This is just a quick view from the equatorial plane looking toward the magnetotail, and you can sort of see the inner edge of one of these features along with a rendering of the XZ plane in SM coordinates. I won't talk about this too much more, but I'm happy to answer questions about that later. The other option is to use some of the geometry of the magnetic field to perhaps see if you can improve the image projection based on that. So what this means in practice is if we have our little friend here and it has a line of sight that lands in the equatorial plane somewhere out here, that line of sight is going to cross a field line which, if we assume these features are mostly attached to a dipolarizing flux tube, means that the location where this pixel gets projected is different from where the flux tube that the feature is associated with crosses the equatorial plane. So the other option here is to project a line of sight straight to the equatorial plane, but without knowing where that pixel lands, you can see that you get sort of a diminished contribution just from this geometric argument of a very simple dipole and polar position spacecraft. So the option that we have here is to take every pixel in the imager, find its line of sight's tangent dipole field line, and simply reproject those within the equatorial plane for all the pixels on a given map. And so here's an example of how well that works. This is a very simple approximation, and of course, further in the tail, you're going to have much more stretched field lines, but you can see that just playing this video back with the same contours from before, but with the blue pixels all reprojected based on this dipole line of sight tangency, the overall match between the ground truth contours and the blue pixels from the imager is far better. Additionally, I've also added a third line to this plot just for the radial position of the feature, and you can see that on the approach phase at least, the green line much better matches the orange MAGE equatorial locations than it did before. So afterward is a different story, but this is just a preliminary result, and so far it seems to be a useful demonstration of how this sort of an Aussie technique, this was supposed to loop, oh well, the Aussie technique can sort of allow you to take a global model like MAGE and use it to validate new analysis techniques such as that can help you improve the localization of where features might be in an otherwise sort of ambiguous line of sight projected image. I won't linger on this slide, but I'll just mention that one of the things I'm planning on doing with this Aussie approach is taking data from previous ENA imaging missions like TWINS and going to do as much of a one-to-one comparison as possible. This is going to require using an instrument response function and many other sorts of things to make the imager a lot more realistic. As you can see, the resolution of these two images differs significantly, and I won't get into it much more than that. So I'll leave it here and just want to communicate the note that this is a very useful tool for doing data model validations. It lets you do potentially put constraints on instrument design requirements in order to observe these kinds of features. And I think that's about it. So thank you.
Thank you, Joel, for a very clear talk. Questions? No questions. I really like how you have used the OSIS to do an analysis that we normally just do for mission, right? So this is really great. Last chance. Thank you so much.
Thanks.
Our next and last speaker is Honan Wu.
Yes, since I'm the last speaker, so I will not go into any of the physics. I just talk about the tools that we have for possible future collaborations that can be used for science. So today I'm going to talk about the tool that I have been developed a few years ago on the extension to TIE-GCM, which is a nested grid extension to the original model. This model has been published on GitHub, and right here I just show some movies of some simulation results to see, to just let you know how it works and what it can provide. For example, in this Tonga volcano eruption simulation, when we add some kind of perturbation at the lower boundary, if we just use the regular original TIE-GCM, the uniform resolution TIE-GCM, we barely see, we can see some structures of the lower boundary perturbation here, but it is not as clear as the bottom row, which is another TIE-GCM simulation, but with the nested grid extension. Basically, in this nested grid TIE-GCM, we implement a hybrid grid approach that solves the physical progresses in two different sets of grids. One is the original global low-resolution grid, and the other is the high-resolution regional grid. And here what I show is 2.5 degree with 1 degree nesting. And well, I'll just let the movie play a little bit until these waves propagate out of this black box. So here, I'll stop here. If you see here in this bottom left, the waves has somehow propagate out of this black box. And if you discard this region and look at the other region compared to the global resolution, that in that case, you will see quite a similar behavior of the model. That means the nested grid TIE-GCM will have big effect inside the nested grid region, but the global response will be still similar. That means we are not changing the whole physics. So what does TIE-GCM solve? TIE-GCM nested grid solve? Basically, it solves everything. It solves for neutral dynamics, neutral thermodynamics, neutral continuity equation, which is the mass transport, and also the plasma transport, and a lot of other chemistry processes. The only thing that is not solved alone inside the nested grid domain is the electrodynamics, which is a Poisson equation. So that is a global equation. We do not intend to resolve it inside the nested grid regional domain. And these slides briefly talked about the technical design of how this nested grid is carried out. I will just skip the details and say that this works. This will work, and it has been used in several studies that can produce satisfactory nested grid simulations. And this is the this slide is the continue of the previous movie, and I just select a longitude and see the TID propagation in this snapshot, in this cross section. So we got really good comparison with GNSS TEC observations, and so the propagation speed of TID is in very good correspondence from our simulation with the observations. And there's another study uses this nested grid. Here we not only use the second use one set of regional grid, but instead we use two set of regional grids. This slide shows the lower boundary perturbation we applied. Here you can see the lower boundary perturbation has this very rich gravity wave structures propagating out, and what we do is here we implement this gravity wave into TIGCM, and this is the movie showing the neutral wind perturbation, neutral wind response inside the nested grid domain. So in this simulation, we go from 1.25 degree to 0.6 degree and then 0.3 degree, which is so far the finest simulation that has been carried out in TIE-GCM. So you see a lot of TID structures propagating out, gravity wave structure propagating out. And this movie shows the the ionospheric responses to the thermospheric gravity wave propagation. So this is electron density. We also see this large, small scale wave propagation structure. That means the small scale gravity waves can indeed propagate into the thermosphere and upward and affect the ionosphere. So here is just a data model comparison. The basic conclusion is that we got good comparison with the data GNS observations. So that ends my talk, and basically what I would like to do is just to introduce this powerful tool that hasn't been really used a lot in the past few years. So if you are interested or have think about a possible project that we can potentially collaborate, please just come and reach me. Thanks.
So, thank you so much. Questions?
No questions?
Very clear. Thank you very much.
Thank you.
So, no, it's late. We know we have at least half an hour to discuss, but we know everyone is tired. So I am going to propose that we close the session here, and maybe we stay around talking and discussing some of the results. But before we go, I want to thank the two students that were helping us with the microphone. So do you want to introduce yourself?
Sure. My name is Jody McLennan. I'm finishing my third year at the University of Iowa as a PhD student.
And I'm Annika Diakovic. I'm also finishing my third year at Boston University.
Thank you so much. And thanks everyone and all the presenters. Have a good trip back home.
There's still another session after this, though, if you're interested.
Yeah, there is a session in this room, too, that is a bit of modeling, but more equatorial region.